For today's video, let us prove a problem using a principle of mathematical induction, or simply as PMI. But before we are going to prove the sample problem, let us define first what is principle of mathematical induction, or the PMI. So PMI is a deductive reasoning which often uses logic, assumptions, and contradictions to reach conclusive proof. It is a way of proving that P of n is true for all integers and is greater than or equal to a. So it works in two steps. Our first step, we have the base case. So for the base case, we need to prove that P of a is true. And the second step, we have inductive steps. So for the inductive steps, we assume that P of k is true for some integer k greater than or equal to a, and use this to prove that P of k plus 1 is also true. So let's try a sample problem. So let's have 3 plus 7 plus 11 plus 15 plus 19 plus and plus 4n minus 1 is equal to 2n squared plus n. So to prove this expression is equal to this expression, let's try it first for the base case. So for the base case, let's try for the first term, and let's have if n is equal to 1. So our first term will be, we have 3. So 3 is equal to, in this expression, 2n squared plus n. So let's prove that it is true for the first term when n is equal to 1. So 3 is equal to 2 times 1 squared plus 1. So 3 is equal to 2 times 1 squared is 1 times 2 is 2 plus 1. So 3 is equal to 3. It is true for the first term when n is equal to 1. And let's have for the second term, and we have n is equal to 2. So for the left side, 3 plus 7 is equal to 2n squared plus n. So 3 plus 7 is just 10 is equal to 2 times 2 squared plus 2. 10 is equal to 2 squared is 4. 4 times 2 is 8. 8 plus 2. So 10 is equal to 8 plus 2. It's just 10. So it's true for the second term. And then let's have for the third term when n is equal to 3. So 3 plus 7 plus 11 is equal to 2n squared plus n. So 3 plus 7 is 10 plus 1 is 21. It's equal to 2 times 3 squared plus 3. 21, that's right. 3 times 3 squared is 9. 9 times 2 is 18 plus 3. 21. 18 plus 3 is equal to 21. So it's true for the base case. So this our base case holds true. And let's proceed to second step. So our second step will be the inductive steps. So let's assume that P of k is true for some integer, okay, is greater than or equal to a. So let's assume that it is true for n is equal to k. So we have let's assume that n is equal to k is also true. So we have 3 plus 7 plus 11 plus 15 plus 19 plus that plus 4k minus 1 is equal to 2k. For n minus 1 is equal to 2n squared plus n. So let's assume that it is true for n is equal to k. So 3 plus 7 plus 11 plus 15 plus 19 plus that plus. So 4k minus 1 is equal to 2k squared plus k. Okay. This n is equal to k is also true. So let's prove that it is also true for n is equal to k plus 1. N is equal to k plus 1 is true. So we have 3 plus 7 plus 11 plus 15 plus 19 plus 4 k minus 1 is equal to 2k squared plus k. And then we prove that n is equal to k plus 1. So 3 plus 7 plus 11 plus 15 plus 19 plus 4k minus 1 plus 4 times k plus 1 minus 1 is equal to 2 times k plus 1 squared plus k plus 1. And for the next part, let's have, since this expression is equal to this expression, so we just only need to rewrite this equation. So 2k squared plus k plus the next term, we have 4 times k plus 1 minus 1 is equal to 2k plus 1 squared plus k plus 1. And then let's combine the like terms or expand the expression. So we have 2k squared plus k. So 4 times k is just 4k. 4 times 1 is 4 minus 1 is 3. So just positive 3. And for the right side, we have expand the binomial. So 2 times k squared plus 2k plus 1 plus k plus 1. Then combine like terms for the left side. So we have 2k squared plus 5k plus 3 is equal to, so just distribute the 2 to parentheses. So we have 2k squared plus 4k plus 2 plus k plus 1. So that's right, the left side. So 2k squared plus 5k plus 3. Then combine like terms for the right side. So 2k squared plus 5k plus 3. Then therefore, this equation is equal to this expression. So this expression is equal to this expression. So we prove that it is also true for n is equal to k plus 1. So therefore, the n is equal to k plus 1 is also true.